All right. So again, thanks to everyone for making this possible. And I want to talk to you about this new assumption, the actual assumption that we need to make that allows us to achieve I/O using the techniques that we've already seen in the last couple of talks. Now, the goal of this talk is to tell you the assumption, and for those of you who have seen, sorry, there's some technical issue. Ah, there we go. Okay, for those of you who've seen me give talks like this before, you should pay attention nevertheless, because it's a little bit simpler. And really the main goal that we're trying to do here is to come up with the simplest plausible assumption, hopefully simplest true assumption that allows us to attain I/O. That's sort of the main research agenda that we're trying to push here with regard to I/O. So what's the idea? As has been alluded to already, we want to leverage the hardness of solving certain systems of polynomial equations over the rationals, over the integers, okay? And we've already talked about how important I/O is and why this is a great problem, so let me not mention that. And the twist that we're going to be bringing here is that typically in crypto, when we look at hardness that's present in polynomial systems, that hardness sort of critically relies on the mod p structure, right? On the fact that we're overflowing mod p and the consequences of that with regard to trying to solve problems. For example, if you're solving systems of polynomial equations mod p, then we can't do nice things like gradient descent, right? So these days the whole world and with machine learning and everything works on gradient descent, and we've been lucky in crypto that people can't use that usually to break our crypto systems because we're working mod p. But now we're going to try to change that around, and we're actually going to try to look at systems of polynomial equations over the integers where we are now subject to new attack possibilities, and nevertheless try to find hardness here and then use it for cryptographic purposes. So that's going to be what we're going to be talking about. What's the good news here? The good news is that even if the attack surface is larger, people have looked at trying to solve polynomial systems over the integers and over the rationals for hundreds of years. This is a very well-studied area in mathematics. And so we're not at least venturing out into completely, strange territory. This is not some weird problem that we're inventing just for the purpose of building I/O, which arguably has been the case in previous works, including my own works, trying to build I/O using multilinear map candidates and things like that. Here we're trying to really aim for something that's natural as much as possible. And as you'll see, that will yield an assumption that I'll be able to present to you in just a single slide, which is sufficient for building I/O. But we're going to do that slowly, sort of building it up conceptually bit by bit. And again, please do stop me and ask questions at any moment. That's very helpful to me. Okay, so we want to look at polynomials over the integers. And we're looking at, in particular, what we call expanding systems. So what that means is that we have n variables, but we'll have n to the 1 plus epsilon polynomials, where epsilon is some small constant. Think of like 0.1 as our epsilon. And the coefficients of the polynomials themselves are bounded. Let's say bounded by some polynomial in n. Okay, so this gives us some set of polynomials, q1 of x up to qm of x. Excuse me. And now what we'll do is we'll choose a vector e uniformly at random from a subset of the integers, let's say from minus n to n in all of the coordinates independently. So IID, we choose coordinates from minus n to n, okay? This yields us a vector e. And now what we can do is we can give the adversary these polynomials. So first just the polynomials in terms of their coefficients, q1 up to qm, and also the actual output, the actual evaluation of these polynomials at this planted solution e, okay? And then we're asking the extremely natural question to start with, of whether the system of polynomial equations is actually solvable. Can he recover E? Okay, and that's the that's going to be the inspiration for hardness that we're going to be looking at. Okay, so in the context of I/O, historically, things like this were implicit in works that came earlier, where the polynomials were only degree 2, and this is something that Rachel alluded to earlier. And now, why should we hope that maybe degree 2 is okay, or why did we hope back then that maybe degree 2 is okay? Well, if we're willing to make some sort of analog to mod p polynomials, this seems reasonable, because if you choose random degree 2 polynomials mod p at random and have a planted solution, there's something called an MQ system that has been studied for a very long time and appears to be very hard cryptographically. We don't have any good approaches for solving these things, let's say in polynomial time. There are some sub-exponential attacks in certain situations, but if we're looking for sub-exponential security, this is a very natural thing to look at. Unfortunately, though, as I mentioned, when we're working over the rationals and we're working over this additional structure that comes from like looking at a subset of the real numbers, then we're subject to an entirely new attack sort of frontier. And that actually came back to bite us in the context of such degree 2 systems. And in a work that we mentioned earlier with the Barak et al., we were able to use the sum of squares paradigm using semi-definite programming, certain kinds of continuous optimization techniques, to actually break such systems in the sense of being able to efficiently compute the planted solution E. So, and it's very interesting that this is a continuous attack. This is an attack that is inherently using techniques from, continuous optimization. And I do want to mention here that the general case of degree 2, solving degree 2 polynomials with these kind of average case, in these kind of average case settings, is actually still open theoretically, even for degree 2. So we don't have complete theoretical understanding of degree 2. However, it is the case that any concrete degree 2 candidate polynomial that we've ever thought of is broken experimentally using the sum of squares semi-definite programming way of attacking things. So we don't know of a single candidate in degree 2 that seems reasonable, and so it seems quite problematic to hang our hats in the degree 2 case. So this is the problem. We're not going to be, if we want to look for hardness that exists over the rationals, then degree 2 seems problematic. And this is some sort of initial warning sign, right? That polynomials over the integers are going to be more complicated and going to present a more interesting attack surface than polynomials mod p. Okay. So,
Amit,
yes.
I have a quick question.
Yeah.
So these higher degree polynomials over the rationals can, in this case, nevertheless, because of LWE, be expressed as MQ over mod P, right? Like degree
Yes.
2 over mod P.
Right.
But probably with a different distribution than considered in classic MQ literature. Is that right? Can you tell us more about that?
Yes, yes. I will talk more about that later on when I get to the LWE part of the talk. Is it okay for me to postpone that for a little bit?
Yes,
yeah.
sure.
Also, Amit, there's a question here. Just a clarification, when you say a candidate, does it mean candidate distribution on polynomials? What would be a
yes,
candidate?
yes. Good. Candidate here means candidate distribution over polynomials and distribution over the planted solution as well. Okay.
Okay.
So yes. So we are in the average case. There are no plausible such distributions that we know of over degree 2 where we can hope for hardness here. Okay. So okay. So again, so we have a more complex attack surface. We have to nevertheless make progress. So one important point I want to make, sort of as a meta research point of view here, is that since degree 2 is broken, we have to add some complexity. We have no option. We can't just pretend that it's secure. That's not an option, obviously. But we also have to be, we have to remember that we're scientists, right? So we should never panic, right? You know, the panic kind of solution would be to let's make things really complicated so that we could feel safe somehow by how complicated things look. That's not right. We're not in this for, you know, we're not selling a product tomorrow that we need to convince someone is secure. We're in this for the basic science. We're looking at the fundamentals of building I/O. So really, we should be trying to do the simplest thing we can do, right? We are aiming for the simplest, easiest to state assumption that we believe is true, right? So let's try the simplest thing we can do. And so there's an obvious simple thing to do, which is, okay, degree 2 was broken. How about some constant degree that's larger than 2? For example, 3 or 4 or 5, or just some other small constant degree, okay? So that's what we're gonna try to do now. Let's fix some constant degree greater than 2. And now ask the same question. Again, I give the adversary the actual polynomials. I give them all the coefficients for these n to the 1 plus epsilon polynomials and n variables. Again, I have a planted solution. That's just chosen uniformly IID in this way. And the adversary learns the evaluations of these polynomials at the planted solution. Can he recover E? What kind of hardness can we hope for here, right? Before we answer this question, this is an average case, conjecture that we're making. You should be asking, wait a second, what polynomials? Like it's not satisfying to say that, well, do there exist some polynomials that cause us to be true? We have to actually get our hands on these polynomials. So let me give you one very simple, specific way of sampling polynomials that we have reason to believe provides us with some hardness. Okay, so what are we going to do? Our polynomials will simply be sums of monomials with certain coefficients. Okay, recall again that the number of monomials, this is index h for the polynomial, that is n to the 1 plus epsilon. Okay. The coefficients, we're just going to sample IID from +1, -1. So to keep things simple, let's do it that way. And the number of monomials that we will have in every polynomial, the size of the summation, which is the size of the set S of H in this notation, is going to be some n to the row. Okay. And concretely think of rho as being something like 0.4. So n to the 0.4. Okay. And epsilon is 0.1. So this is how we sample our polynomials. We pick n to the 0.4 monomials at random, multilinear monomials. We pick the coefficients uniformly from +1, -1, and that's it. That's our polynomial, okay? And now I am asking that with this specific set of polynomials, with a specific way of choosing this planted solution, is it hard for the adversary to recover the planted solution? And more generally, what kind of hardness is present from such kind of polynomials? Okay. And indeed, we're conjecturing this is hard, and this is going to be like the starting point of the assumption that I'm going to tell you about momentarily. Okay. So, of course, the first question we should ask is, wait a second, we have this very problematic algorithm, the sum of squares algorithm, that broke the degree 2 case. What about that? So this is something that is nice, that we can say that in some new work with Barak, with Boaz, Ayush, and Pravesh Kotari, we can actually prove a lower bound that rules out sum of squares attacks for this specific conjecture. So specifically looking at this particular class of polynomials, this particular way of choosing the planted solution, we can actually prove that the sum of squares algorithm will not be able to break it. And this is important because the sum of squares algorithm, first of all, is the main, boogeyman that we've faced with regard to previous attempts of this form in crypto. But more generally, the sum of squares algorithm is a very powerful technique that has sort of felled a number of important approximation problems that have come up in the approximation algorithms literature, where sum of squares gives the best known results, and there's a whole industry in the sort of stock box community of investigating sum of squares algorithms, sum of squares lower bounds, as providing significant evidence for hardness, at least in other scenarios. So so that's, this is one good thing that we can use to get some confidence that we might be onto the right track here. Okay. Nevertheless, absolutely, this is just the beginning. We want to posit these natural conjectures. We want more cryptanalysis, both theoretical and experimental. And this is an ongoing effort. And I definitely want all of your help. That's one of the objectives of giving talks like this, is that we want to be able to gain confidence in these simple conjectures so that we can then use them cryptographically. Okay. And there's a big target on our backs also, right? So now we have multiple crypto and Eurocrypt papers that would be broken if you can break this assumption. So please try your best to do so.
Amit, quick question.
Absolutely.
Is there a reason why you sort of describe this in terms of degree 4 polynomials as opposed to degree 3? Is it just
Nope. It's just for simplicity. If you had asked me to please open up other things that I'm going to be saying in a moment and tell you how we actually do it, then it's easiest for me to show that in the degree 4 case. I won't have time to do that anyway, but that's the reason, so that I would be able to kind of tell you what's going on. No, I'll mention it later on, though. Thanks for asking the question. I will briefly mention why I was picking at degree 4 right now, but there are similar such families that we can define the degree 3, degree 5, any constant degree, for which that same lower bound will actually apply. Okay, but just for concreteness, I'm looking at degree 4 here.
Yeah, thanks.
Sure. Okay, so great. So I do want to point out we already have a very natural conjecture. This is a super nice conjecture. Please try to break it. Let's see if there's hardness present here. Okay. Unfortunately, this is not enough to get obfuscation. As also already kind of alluded to by Rachel earlier, we will need something to do with LWE here as well. And I'm going to talk about that now. I also want to mention that in addition to the new assumption I'm going to be talking about, we're also going to be assuming sub-exponential security of standard LWE and SXTH over bilinear groups, but those are much more well-studied problems. I'm not going to talk anymore about those in this talk. All right, so without further ado, let's go straight to the actual assumption. So we all know LWE. Let me just set up some parameters. So I'm just going to, I picked these parameters earlier so that I could reuse them. So let P be a n to the 0.4 bit prime. We'll let chi be a discrete Gaussian centered at 0 with standard deviation n. And that gives us, the natural way of sampling LWE samples with, AI being sampled uniformly from ZP, from Z mod P, and with dimension n to the 0.4. And then, we either get this LWE sample where it's A.S plus E, or random, and, LWE asks that this looks pseudo-random, right? Mod P. So again, I wish that we could build IO from this. Of course, we do not know how to do that. And we need to add a little bit of complexity. And the main idea is just the following, that in addition to these LWE samples that the adversary typically gets when we're talking about LWE, we're also going to give the adversary the output of these polynomials evaluated on these EIs. So the only thing I really switched around here was the error distribution. Here I'm talking about a discrete Gaussian, where earlier I was talking about uniform from minus n to n, but that's really the only change that I've made. And another important point here, right, is that we are giving out in this situation n to the 1 plus epsilon evaluations of these polynomials on this error vector E, right? So information theoretically, the error vector is being revealed by these evaluations of the polynomials. So what we're asking for here is that despite that is true, because of the computational hardness that we expect to be present from looking at these evaluations over the rationals, we nevertheless want there to be some security in the LWE setting. And exactly what do I mean? This is the exact new assumption. The version I'm presenting here is from the work with Ayush, Rachel, and Matt, and then also, and then this new simplest version is from the later version with Ayush and Rachel, where again we have our prime, which is n to the 0.4 bits in length. We have our secret s, which is also in dimension n to the 0.4, and we have our our errors e1 up to en. Chosen from this error distribution. And now what we'll do is we'll look, as I just mentioned, at the LWE distribution, this AI comma a dot s plus e, together with this leakage, the evaluations of polynomials on the planted solution e, on the error vector e, which is now the planted solution. And what we'll look at in addition to this is another distribution, which is exactly the same as what we had before. The only difference is that I'm going to add some small perturbations to these outputs of the polynomials that I mentioned. Okay, and the perturbations will be very small. They'll be bounded by, let's say again, n to the 0.4, just to make things simple. And what we ask is that there's a little bit of indistinguishability between these two distributions, meaning that no efficient adversary can distinguish between D1 and D2 with advantage, let's say, greater than 99%. Or more precisely, as Ayush was alluding to, it could be 1 minus 1 over lambda, but just to keep things simple, let's just talk about 99%. And again, I want to emphasize that this is a very weak assumption from that point of view, in the sense that even if there's an adversary that can distinguish between these two distributions with probability 99%, but no adversary can distinguish with probability 99.1%, then the assumption would be true. Okay, so that's all we need from the assumption to get things to work. And why is it that we can handle, such a weak looking assumption with regard to advantage? It's exactly because of what Ayush talked about, right? So when we use this kind of an assumption together with the techniques that Rachel was talking about, then we would get an FE scheme that would also have some sort of like 99 or 1% security. And then we would be able to apply the security amplification theorem that Ayush just mentioned to get it to amplify from that all the way to functional encryption for circuits, which then we could use to get all the way to IO. Okay, so
Amit?
Yes.
May I ask a question? So in the previous version of this that I've seen, maybe from JLMS, you also had in these polynomials, aside from the error terms, you had these two extra variables which were secret.
Yes, absolutely.
Right?
Yes,
and those were, since those were never leaked at all, since they were always in the exponent, they were helping with security.
Right, and in earlier versions, we really needed that. Like that was something that was being used to be able to sort of make things work. But now we've been able to simplify it further. And I want to make that clear. The reason we've done that is not for security. So the point is that indeed we can add 2 more variables that don't get leaked at all, and that's all we actually need for security. But our objective here is to come up with the simplest assumption that is plausible, that we think is sufficient. So that's why I've done that. Because
I see. So it could be that adding those, so if it turns out that, this is somehow problematic, we could go back to adding those and then look at it
absolutely.
again.
We do have more room for here with the techniques that we've developed so far in the previous works, and also in some of these newer works. But the objective is simplicity.
Yeah, sure.
Right.
Okay, yeah, thanks. I was just wondering why you took them out. So it's a conscious choice just to make it simple.
Absolutely, yes. It's just to make it as simple as possible, because this is the assumption, right? And one of the main problems that's existed in our field, for building I/O, is that just writing down the assumption that was needed is usually very complicated and takes a long time. So I really want to minimize the number of variables, minimize the number of things that are in play.
So, Amit, regarding simplicity, I'm a bit confused here. Something very basic. Why 99%? I mean, this would be equivalent to indistinguishability. Oh, wait, there's something else going on here. Because we know that we can just amplify hardness. So why 99 with all equivalent if they're just indistinguishability of distributions?
Okay, right. So first I want to mention that, as Ayush talked about, although he didn't have time to sort of get into the real nitty-gritty details, the security amplification theorem here is quite non-trivial. It's not something that is straightforward by any means. There are a number of things that have to be done to allow us to do this. So I want to mention that
these distributions are efficiently generated, no, or not?
These are all complete. The ones that are on the screen right now are all efficiently generated. Absolutely. Right.
So then they're just like Crypto 101. I mean, it's 99% is the same as any other constant up to.
No. It's not. So sorry. Any other constant? Actually, no. Even that's not true. So no. It really does matter what we write here. And let me make a couple of observations. First of all, note that, as Rachel mentioned earlier, because the output of these polynomials are polynomially bounded, right? And these adversarial perturbations are also polynomial, there will be a 1% distinguisher. Okay, there will be not 1%, there will be like some 1 over n to the something distinguisher, right? There is actually a non-negligible distinguisher between D1 and D2 that follows just from the fact that the sizes of the outputs are polynomial. So the fact that we need some kind of amplification is inherent here.
So I assume you're then assuming that there's some bounded number of samples that you get, because otherwise I can just amplify if I have 1%. If you just talk about standard notion of this indistinguishability between distributions.
The number of samples is n to the 1 plus epsilon. So I guess it is bounded, and that's.
Yeah. No.
I see. So that's the point.
Right. So that is also a point that we have to look at the parameters carefully to make sure that we have the kind of sublinearity that we need. Right. But I'm also just taking issue with the premise of what you're saying. It's not obvious how you can amplify an adversary in this situation, right? The point is, if you give me an adversary that can distinguish, let's say, with probability 1%, I don't know that that gives you an adversary that can distinguish with probability 2%, right? So here, it really does depend on where exactly that boundary sits. And by making the assumption so weak that we would be happy with an adversary that could distinguish it, even probably 99%, is important for gaining confidence in the assumption.
But what you're saying makes sense when there's a bounded number of samples, because if it's just I press a button, I get another sample, then I can definitely take an adversary that distinguishes 1% and amplify it because I get samples. Yeah.
Yes, absolutely. Yeah, it's definitely okay. Now I understand what you were saying earlier, and you're definitely right. Obviously, we are talking about a bounded number of samples, and this 99 is
so that's the point.
the 1 plus.
I guess if it were unbounded, you could just linearize and solve. So it's really important that the number of samples are bounded.
So what's, I guess maybe the way to say it, what's indistinguishable is the two distributions which have some n to the 1.1 samples from what's written here.
Yes, absolutely, and I'm happy for all the questions, but I want to mention just a few.
Sorry,
about why we think it's secure. If it's okay for me to
we over time, but sorry, maybe a couple more minutes.
Okay, excellent. So So first I want to mention that despite the fact that we've added all this LWE stuff here, really the most plausible way we have to attack this problem is still actually by trying to break the polynomial inversion problem that I mentioned earlier. And why is that? It's because it's actually very hard to make use of this LWE stuff that is being given, or so it seems. Let me talk to you a little bit about what we've thought about. So as Shweta just alluded to, the first and often most deadly foe for those of you who have, tread this path like I have, where we're trying to look at variant assumptions, are just linearization attacks. So here, the parameters really matter. And it's very important that we've set parameters the way that we have to make sure that there aren't linearization attacks. We can't just take, for example, our degree 4 monomials and replace them all with linearly, like just with new variables, and nevertheless solve the system of equations. So, so we've looked at that very carefully. That's the best that I can tell you. And we're not aware of any linearization attacks. And again, this stuff has been published for a while and no one has found them. So we're definitely very aware of that and have thought about it, but we're not aware of any linearization attacks.
So, Amit,
yeah.
Really quick question, if I may. So the assumption, QL are degree 4 polynomials, and they are public degree 4 polynomials, or?
Absolutely, yep, completely. They're chosen. They can be chosen at random, but then they're published once and for all.
Okay, sounds good.
Yeah. And again, I'm just giving you one distribution because I want to make things very concrete, especially for the cryptanalysts in the audience, who I really want to try to attack this. But we do have flexibility. We do have significant flexibility in how we choose these polynomials.
Okay.
All right. So, so what can we think about here? How can we potentially make use of this LW information? Well, one thing we can think about is by going back to equations mod P, right? So, if we have LWE samples, we can observe that we can write the errors as being, bi minus ai dot s mod P, and therefore we'll end up with polynomial equations in S over mod P, right? So we also have to make sure, and that's why we had like 0.4 and 0.1, like these parameters matter, that once we do this, once we turn them into equations over S, which remember was only n to the 0.4 dimensional, I still need to make sure that there's no linearization attack. And with the parameters we've chosen, we do, in fact, guarantee that. We can try to think, how can we solve these equations mod P efficiently? And again, there is a long history of work here. The only thing I'll mention that we can say right now is initial observation, where if we look at, for example, Grosvenor basis attacks on these kinds of polynomials, then with the parameters that we've chosen, it would still yield a sub-exponential attack complexity under a non-trivial assumption, an assumption that these polynomials that we end up with, as written here, are semi-regular. They have the semi-regularity property, which is just a conjecture that is typically made for analyzing Grosvenor basis attacks in many settings. Is that true? Unclear. In general, it's a huge open question to be able to prove semi-regularity of any particular family of polynomial equations mod P. But that's a common assumption that's made. And in that case, we would be able to show that the Grosvenor attack would still be sub-exponential in complexity. Again, this is just the beginning of work in this area. Please help us attack these things. This is like one avenue for attack.
Amit, one more question, if I may. The size of S, the dimension of S is, how does it relate to N? How should I think about it?
It's n to the 0.4 in the example that I'm giving.
And degree 4 polynomials.
Degree 4 polynomials, yes.
Okay.
Okay. And again, that is important, right? We have to make sure that linearization attacks don't occur, and that's why we're choosing them in this way here. And that was also, by the way, Shweta, to kind of come back to your question, the reason why we were able to get rid of those additional variables that we used to have in the assumption is by being very careful with these kind of parameter choices when it comes to the choice of row. Okay. And there are tons of open questions here. One of the most fascinating ones is, are there is there any intelligent way to make use of this degree 4 or in general constant degree leakage with actual lattice reduction attacks? And it's fair to say that we have no idea how such an attack would work. And the idea, the bottleneck is straightforward. It's just that lattice-based reduction is essentially about linear algebra, and it's just unclear. How can we make use of higher degree information in any intelligent way with lattice-based reduction techniques? I have no idea. I've thought about it, and I would love for you all to think about it. Another thing that is open, if you just come back to this more basic question of just can we do polynomial inversion, is, for example, can we get a lower bound ruling out gradient descent, right? We definitely have experimental evidence for this. We've tried gradient descent and it doesn't work when you go beyond degree 2 experimentally, but that's just experiments. It doesn't tell us what is the asymptotic behavior very precisely. Surprisingly, even though someone could have asked this question in the time of Newton, it is an open question. We don't know any way of proving lower bounds for gradient descent. This is just a beautiful question that I would love to for someone to think about. And then other evidence of attacks or other evidence of hardness would be great, maybe from a statistical physics perspective. Statistical physicists have looked at hardness of various problems that arise in their domains in various heuristic ways. Maybe those kinds of heuristics can apply to our setting as well. And I again want to mention that this is now published in multiple crypto Eurocrypt papers. It's a big juicy target for cryptanalysis. Please try to break it. Of course, the big open questions here, there are many of them. What I've talked about so far is inherently about using these kinds of pseudorandom objects over the integers. Can we somehow use LWE, but now in combination with Boolean PRGs instead of PRGs over the integers, and still be able to use it to get IO? I think that would be really interesting if we can do it.
So why is that better? Just because they've been studied more?
Yeah, because they've been studied more. So even though it's really exciting, I think it's really fun and cool to think about hardness over the integers. We do have much more years of evidence of hardness for Boolean PRGs, even with low degree polynomials that are computing those Boolean PRGs. So that would be cool to be able to nevertheless exploit that to be able to get an IO construction. Can we somehow separate LWE from a polynomial hardness assumption? Can I have an assumption where I just assume LWE and then separately a polynomial inversion assumption? That would be awesome. Excellent open question. And then I've already promised at least $1,000 out of my bank account for an actual construction of IO from LWE. This is the big white whale here, which we would love to solve. And
what do those? There are these lower bounds, right? That about how you cannot get IO from all or nothing primitives, and therefore LWE is unlikely.
Right. I think that's an overinterpretation of the lower bounds, in the sense that all of these bootstrapping techniques are highly non-black box, and the particular kinds of non-black box techniques that are ruled out with the lower bounds that currently exist are limited. So given that we're already doing lots of non-black box stuff, I don't see that as being particularly good evidence that IO from LWE should be hard to do, or should be impossible to do at all, actually. It just means that we will have to use novel non-black box techniques, but we're already doing that.
Amit, you try to wrap up?
Yes. So I was going to end with my garden slide, just to talk about the importance of new assumptions in crypto. But since we're out of time, I'll just leave it up here and end here. Thanks so much.
Thank you. So since it's the last talk of the day, I mean, we can just hang out, ask questions who everybody wants. So there's one still question that is on the chat. Let me just read it. Can semi-regularity be tested experimentally, and has this been done?
Good question. So the answer is not satisfactorily yet. It's something that we're trying to do right now. If you're interested, then please talk to me. I would love to work on this with other people as well. Again, the evidence that we would be able to achieve experimentally would be limited, but it would still be something, and it's worth doing, and we need to do it, and we haven't done it yet. That's the answer.
Anybody else?
So again, what would that just to for people who don't know what that means? What would that mean? What that would mean is we could just set up these equations and start running Grosvenor-Based algorithms on it. Right now, these algorithms do take a long time, but we can run them for certain settings of parameters with the machine, and then just see what is the maximum degree of the intermediate computations that we see during that Grosvenor-Based computation, and then compare that with what's predicted under the assumption of, say, some irregularity. And that is something that we can and should do.
Okay. Okay. Thanks again, Amit.
All right. Thank you.
You want to say a word about tomorrow?
Well, thank you, everyone.
What about the food? The food has been great so far.
All right. Thank you all the speakers and to all the session chairs. So we'll continue tomorrow. Thank you. Bye-bye.
Okay, thank you.
Bye.
Thank you.
Bye.